Okay, so let's make a start. So it's a great pleasure to welcome Paul Hearn this evening, who there's a clue on the Zoom there. He's come to talk to us about radio astronomy and also give us an introduction not only to radio astronomy but the Radio Astronomy Association. So a very warm welcome. Thank you for joining us, and I'd like to hand over to you. Thank you very much.
Thank you. Thank you very much for the warm welcome. Yeah, I can see why the club is successful. Two things I just picked up. One, your concern for your sick friend. That's great. And also the comment our friend here said about bringing alcohol. Really important. So I think in 100 years' time, you will still be around. Thank you for inviting me this evening. The picture I got there, just for the projector setup, is quite interesting, and we're going to start with this and probably finish with it. It's a heritage site in Germany, in fact, the first radio telescope in Germany, and it's now run by an amateur club. And they have lots of collaboration with academics, and they actually run MSc courses with Zurich University from their club. So I think, you know, if you can get things right in the amateur world, then it's surprising what can happen. And I was really encouraged to hear that there's 80 members here. I'm absolutely sure you'll be around. If my life had turned out even a slightly bit differently, I think I would have been sitting there with you, because as a young teenager, I put together a diode, and one of those, radio isn't really my thing, but those variable capacitors with the fins that interlock with each other. So that, and then a long antenna running down the garden to listen on ex-government. Do you remember the shop on the bridge? Fantastic place. Yeah, I got some metal headphones that were really uncomfortable. But as a 13-year-old, I could listen to Radio Luxembourg with just about a 3-component diode, and there's one other thing. Yeah, it was fascinating, and now my life took a slightly different turn. And I've taken up radio astronomy only since 2018, but it has just captivated me. So yeah, I'm not, that didn't work. Why won't it advance? The meeting is being recorded. Oh, I see, got it. Yes, here we go. What really captivated me was how much real science and observation can be done with very little. And tonight, I'm not going to talk, I will be talking about radio astronomy, but it'll be biased to what we can do and what I do in a shack. Do you use that word still? Shack? Yeah, okay. Yeah. Shack. So I'm not a scientist. I'm a retired engineer, and only, as I said, 2018. And thank you for inviting me this evening. So we're going to have a look at what can be built at home. So it'll be less pure radio astronomy and astrophysics, and it'll be a brief journey through the electromagnetic spectrum. I use the term amateur and independent researcher interchangeably, because amateur has with it certain connotations which are just not right or true in your context or in the world of radio astronomy. Yeah, it's more of a chaotic leaping than a brief journey. But I don't want to start with something that I only discovered recently, and you may well have come across this, but you will have seen these very ancient cave paintings in France, and it was pointed out to me that that not only were the animals anatomically correct in their structure, in their drawings, but also there were with not, I don't know if my, yeah, oh, yeah, it kind of works, doesn't it, the laser thing. Without too much imagination, we can see the constellation of Pleiades. You need a bit of imagination to pick up Hades, and Orion's belt has got 4 rather than 3 spots. But it was clear that there was some observing going on of the universe way back. This is 14,000 BC, and it was pointed out to me as well that maybe over the period of time that those drawings were being made, that a planet was traversing across the sky. So it's like time domain observation from the ancients. So I just throw that in because I think it's quite interesting that we find ourselves a part of a history of observing the skies. It's an excuse to show some classic images. We saw this one a few years ago. Massive amount of money and lots of scientists, and I think 2 of them got a Nobel Prize for producing that image, radio astronomy. And then just today I noticed at 6 o'clock, and from our own galaxy, it's been imaged, the event horizon from the black hole. No talk about radio astronomy, and I think you had my friend Brian Coleman, and he may well have shown this. Every talk I've been to that talks about radio astronomy shows this slide, and I think the founder, Karl Jansky, only ever had 1 picture taken of him. But he is known as like the founder of radio astronomy. He was working for Bell, well, the Bell Labs now, Bell Telephones, Bell Communications at the time, and there was noise that he was picking up on their transmission lines, and it turned out to be not from any of their systems, but from outer space radio. And then this is the classic image, another one that radio astronomy brings to the party, because in the 60s I followed the Horizon documentaries, and there's always this debate about the origin of the universe. Was it a big bang, or was it a kind of a cyclic? And of course, radio astronomy with this particular image of the microwave background that's ubiquitous was informing the decision of the hypothesis that, in fact, all the matter in the universe was at one place at one point in time. And of course, other evidence is that we can see the universe is expanding at an exponential rate. And that also, coupled with the radio astronomy observations, would lead us to these to answers to these massive questions about our genesis and the universe. Okay, I've got a few images here of the Crab Nebula, and they're of it's the same object in the sky, but at different wavelengths, showing us completely different things. So that's an X-ray image. We've got an ultraviolet image, something that classical astronomers have been more familiar with, just an optical image. And then the radio image at much longer wavelengths, describing something of the electromagnetic interaction with electrons in the object. Okay, this is something that you'll be a lot more familiar with than I, but it does demonstrate that radio astronomers are struggling with very small signals, and broadcast signals we can see here at the power density watt per square meter hertz at 10 to the minus 13, but we're another 10 orders of magnitude plus from that. So try to sort out the noise from the signal to generate images, to come to conclusions. It's always something that is a real fight with radio astronomers. This is just a little bit of background and context, and I'm sure you will be very familiar with this image. I just want to grab a pointer from my case. Here we go. Yeah, so at the very short wavelengths, we've got the gamma rays and X-rays, and then coming towards the ultraviolet, and then this is the little bit that the optical astronomers are observing from the sky. The radio astronomers are able to work in this band here, and the very long wavelengths are blocked by the atmosphere, as is the very harmful X-rays, ultraviolet, etc. Right, now then, what we can do, and I think this might even be, yes, this is today. So we can collect very easily from NASA data from the X-ray flux from the sun. And that becomes relevant because many of the observations that we can do are related to what's happening in the sun. And to correlate those observations with the X-ray data is something that is quite useful. And we'll come back to that. We'll come back to that in a moment. During periods of activity, and I'm talking about the sun here because the signals that we can get and process with techniques associated with radio astronomy are really good at describing some of these events from solar activity. And there's massive, I mean, the sun, it sits in the sky and it's beautiful and it looks quite passive, but in actual fact, it's incredibly violent. And from time to time, there's a mass ejection of vast energy, electrons and protons and natural radio, and there's just a load of stuff that can be measured and correlated. And we'll have a look at that in a moment. And as I say, this is important because it can be easily observed, readily observed by us in our shack. And I include this because when we have this violent solar activity, then it can have an effect, and we can, we're familiar with the aurora. But there's also enhanced radiation, and someone not muted. NASA monitor the solar activity because they don't want their astronauts to be spacewalking at a time of high radiation from the sun. Passengers and crew and airlines are exposed to higher levels of radiation, particularly at times of solar activity. Satellites from time to time have to be shut down so they're not damaged by these violent solar events, and we can get power line disruption and all sorts as well. So they have been, in recent years, added to the National Risk Register, which over the last few years we've heard quite a lot about. But solar activity is also a part of that is monitored for all of these very good reasons. This was just today, 6:15, before I went in to see the news that they just imaged the event horizon of our solar system's black hole. So there's a bit of activity today we can see from the sun, and some of these may produce flares where the Earth's magnetic field, is disturbed, where enhanced natural radio, is that? Okay. Where there's an increase in natural radioactivity, where there's an increase in cosmic radiation, and well, I've got a little detector here, so I'll show you about that in a moment. Right, so nuts and bolts, getting down to it now. What can the independent researcher do? Okay, so at the beginning of my list, we've got a meteor observation by forward scatter. And we'll have a look at that because that's particularly relevant just at the moment because, what day of the week is it today? It's a Thursday, yeah, Thursday. So on Saturday, the RSGB and BAA joint project for forward scatter meteor work, the beacon for that will be installed. But I'll say a little bit more about that in a moment. Sudden ionospheric disturbance. So this will probably affect some of the stuff that you do. The solar activity will affect the geometry of the upper atmosphere. And very low frequency radio propagation is also affected by the geometry of the upper atmosphere. And so if we're monitoring a station and the amplitude of the signal is changing, then that will be as a result of solar activity. Geomagnetic observation. So again, this is another of these effects that can occur because of solar activity and extragalactic activity to a much lesser extent. Solar natural radio spectrometry. Mike was helping me with a setup in my lab at home at the back end of last year, and we'll have a look at that in a moment. Cosmic radiation detection by muon counting. Again, this is quite a new project, but a number of us are building detectors to do that. And again, we'll look at that in a bit more detail in a moment. Hydrogen line observation. Brian was with you a year or two back. It was pre-COVID, wasn't it? And this is what he does at home. And he has not that one, but a 4-meter dish in his front garden. Pulsar observation. Again, that can be done from home with relatively modest kit, but very sophisticated signal processing because of the signal to noise ratio that we're struggling with. And again, we'll look at that in a moment. A fast radio burst. The very first slide I showed you from our friends in Germany, they are working with the academic community because fast radio bursts, you have to be looking at the right place at the right time for just a few milliseconds. And a massive amount of energy across a very broad band of radio frequencies. And the origin and how they're generated is still a bit of a mystery. But the independent observer with the right kit can do that. Okay, so this is my setup at home. I just quickly go through this. Got muon counting, code. The independent radio astronomer comes into the hobby, if you like, into the field because of an interest in building stuff and getting it going. Much like every one of you here, I imagine, and also writing code for deconvolution and visualization, etc. We've got geomagnetism down here, getting the X-ray data. That has to come from a satellite because you remember the spectrum we showed at the very beginning with the very short wavelengths where the X-rays sit don't penetrate the atmosphere. which is good. Sudden ionospheric disturbance, and yeah, more code. Spectrum Lab. Do you guys use Spectrum Lab? You come across Spectrum Lab? So I think it was written for amateur radio enthusiasts. Okay, so I'll have a look at some of these. Forward scatter meteor detection. So what's happening here? When a meteor, and these are particularly interesting because they can come from outside our solar system. And that's why there's a lot of excitement when there's a meteor that's big enough to come through our atmosphere and land on someone's drive and then be picked up by planetary geologists, because that material may well have come from outside our solar system. But more often than not, the particles are very, very small, but they leave a trail of atmospheric destruction of positive ions and electrons. And as you will know better than I, that this can reflect radio waves. So if we are set up and tuned to a transmitter, then we can get a ping, and we can determine all sorts of things from the echo from the meteor. Yes. Right. Yes. Yes. Right. Yes. Interesting. Why?
Yeah, I'm just asking why the ionization happens.
Okay, the meteor will have a phenomenal amount of kinetic energy, and as it impinges the atoms in the upper atmosphere, then there's an equally massive deceleration, and that dissipation of energy causes basically the atoms in the meteor. That the whole thing will vaporize, and in that vapor, the electrons get stripped off from their host atoms, and then they recombine, and so the event disappears. Yeah, exactly that. Yes, it's exactly that. Up to now, maybe up to tomorrow, it was this transmitter in France, part of their air defense system, that was used at Graves, because it's a very strong transmitter at 143 megahertz, and it's relatively it's so strong we can pick it up here, and the geometry is such that in the UK you can pick up the meteor information, but the whole thing is very complex. It's scanning and pulsing, and and sometimes it goes down for maintenance, and it's not very good if you're trying to determine specific characteristics of the meteor event to draw conclusions about upper atmosphere. Yes.
So it would then show you a graph that was in a sort of pseudo 3D thing that actually would show you frequency spread and the time of when it happens. And it used to be very useful to monitor that site because you could determine some idea about meteor rates, because the higher the meteor rate, the more successful you are likely to be in making a contact. If you've got a random rate of one meteor, say only every 5 minutes, you'll lose patience before you make a contact. The longest I've had a successful contact, it's taken me 45 minutes to make one contact because you're just waiting for the next meteor ping, and it has to be in the right position to support the communication between the two stations. So, and sadly, that website has now closed because it's expensive to run, and the guy simply couldn't afford to fund it on his own basis, and couldn't get enough funding from crowdsourcing and so forth to keep it going. So, a bit sad.
Yeah, I think we're talking with him. What's the name of the site? Can you remember?
I think if you looked at something like real-time meteor scatter, it would come up
It'll-
with
yeah, I
one of
think-
the very early.
Yeah.
I think, and I suspect it was probably leveraging data from the Dijon transmitter, but probably from a number of independent
Yes,
receivers.
Brahms as well. Yes.
Yes.
Yes. Yeah, so that's just a very simple antenna that I built when I was looking at doing meteor observations from Dijon. And yeah, as you'll know better than I, you don't need very much. You don't need very much hardware. Just an antenna and a SDR. And then what the meteor observers do is count events per hour and then fill out a chart like this, such that we've got one square for each hour of the day and then one column for every day of the month. And these are and these tables are collated. There's an archive of these that people can interrogate if you're interested. And then the kind of data that we get, where this is frequency and this is time, and these are just four examples. And the frequency spread we can see on here is quite significant, and they don't last very long, as you just pointed out. Yes, they're very short. Yes, exactly. But the project that's just starting between the RSGB and the BAA is looking at understanding particularly what the head echo is telling us about upper atmosphere, the condition of the upper atmosphere, upper atmospheric physics, and looking at Doppler shift between the same event but observed at different locations, so it can be identified, and then that data correlated with the visual observers. I think my next slide.
Direction from which the meteor came.
Yes. Yeah. Yeah, this was the project that I was just. Yeah, hang on to it. This was the project I was talking about, and I don't think it's quite gone live yet, but it's very. I think the website might be, but it's not doing very much just at the minute because the beacon isn't going. My thingy has stopped thinking. Oh no, the computer has. The slide has, in fact. I don't know. The computer is. Should I just log in again? It's a Wi-Fi issue, is it? It's just, okay. So what the meteor observers would really like to do is identify where in three-dimensional space that event is, and then correlate that with the people that have built all-sky cameras. So for very little money, you can have a camera connected to a Raspberry Pi just picking up just photographing the sky every couple of minutes, and then we can see all the meteor events for that evening, And what they want to do is try and correlate a radio observed meteor with a visually observed meteor, and then with enough observations, track it in three-dimensional space. And then if it's a big enough meteor, then and it gets to the ground, then it can be found. And as I say, the planetary geologists get extremely excited. You remember the one that landed last year and went to the Natural History Museum.
I think there was a crew that came out with angle grinders and literally cut out like a square meter of somebody's drive.
They did, yeah. They took it in situ. Yeah, yes, that's right. I think my phone is still going. Is that another solution? Okay, we're bearing with you. So the yeah, there are lots of possibilities there, because there are academics as well as independent researchers bringing this data together. And I think only, was it last weekend or the weekend before, there was a meteorite that landed somewhere in Shropshire, not yet found. I mean, it might be only an inch or two, but they're still looking for that one. So the next part on my list of things that can be done at home, as it were, was sudden ionospheric disturbance. Now, you will know that the military maintain transmitters in the 15 to 35 kilohertz range for talking to their submarines. And these, at these frequencies, they're very sensitive to changes in the ionosphere. So when there's a geomagnetic event, then the upper atmosphere can become compressed. And even with a fairly crude radio, you can see the change in gain on the signal. And that can be correlated with the X-ray data that I showed you earlier. It can be correlated with cosmic radiation, which we haven't looked at yet, but we will in a very short time. So it's quite interesting to see these different phenomena observed and then the data brought together.
So for these sudden
atmospheric, yes,
yeah. How much of that is influenced by changes to the Earth's magnetic field as a result of being hit by CMEs and the like?
Well, I think the greater effect is changes to the D layer in the ionosphere.
Right.
Yeah.
Because the D layer is primarily, it has a very absorptive qualities rather than refractive qualities. So yeah, it makes sense.
Yeah. And it's interesting that if we're looking at these sudden ionospheric disturbance effects at those frequencies, then sometimes there'll be an increase, and sometimes at a different frequency, because the transmitter's in a different place, there'll be a decrease. And what we're looking at there is changes in the path length of the reflected radio wave as compared to the ground wave. We don't understand there, get blinded. And so there's a phase difference between the two. And I've got some examples of that we'll look at in a moment once we got comms re-established. So the meteor observation and sudden ionospheric disturbance are quite common pathways in for the new radio astronomer, because without, as I said earlier, without very much kit, you can do quite a lot. We then move on to magnetometry. So the solar activity will affect the the geomagnetic environment. So with a magnetometer, it's relatively easy to measure that. And again, we can data log over a period of time and see genuine changes to the geomagnetism as a result of solar activity. And that could be correlated with the other observations that we're making. How are we doing? Ah, yeah, well, that's where we left off. That was the next slide.
Yes, I know of one German amateur that has built his own magnetometer, and he actually has a website that shows that as real-time data.
Okay, yes. Yeah, there's a number. But this was, this is the transmitter that is being used for the UK beacon, and it's a Moxon 6-meter transmitter for it, and it's going to be located at Sherwood Observatory. So they have quite a lot of public funding and do a lot of outreach, STEM outreach. They run courses for youngsters, scouts and guides, Boys Brigade, etc. Visit. They do school visits. It's very active. Another great example of a club doing good stuff. Anyway, they're going to host the transmitter. It's GB3 MBA, meter observation. I can't remember what it is. GB3 meter. Yeah, very, very good.
Either that or much bigger amplifier.
Much bigger amp, yeah. Okay, then I did briefly talk about the all-sky cameras. So we can see here these are astronomical objects in the sky just as the Earth's rotating. But these, over a period, I think it's 24 hours, it was a meteor shower. This little camera looks like it's a Raspberry Pi sitting under there. Has picked that data up, and there are a lot of people doing this, and the data gets uploaded to a common database, and it's the correlation of this data with the forward scatter radio data that they're hoping to bring together. Okay, we've had a look at some of this. Sky waves and ground waves we've already looked at. Oh yeah, that's a little box that UCRA sell for this very purpose. In the introduction of your colleague here, he mentioned the United Kingdom Radio Astronomy Association, and we exist to design, build, and sell bits of stuff like this, or increasingly bags of bits, kits that people can put together.
So what frequency are you monitoring? I noticed there's a loop antenna.
Yes.
There. So what sort of frequency are you monitoring?
These would be in the range of 15 to...
So we're talking sort of 15 kilohertz, I assume.
Yeah, 15 to 30. I think 45 is the top.
Yeah. Have you had any? I mean, one of the notorious things that is a scourge on us, and I assume.
Have you got a mic? Oh, you have. Good. Yes,
on you as well. Is interference from things like LED lighting, and the sort of noise you get at VLF is considerably worse. Does that kind of impact your observation?
It does. Yeah, I haven't. I don't observe at this frequency yet, although I'm currently building a data logger to do just that. So I'll find out. But it's very dependent on your location, of course. So some will get away with it, others won't. But that's one of the things that UCRA that UCRA sell, and we have a number of schools and colleges that are purchasing kit like this for their students, because there's a whole lot of science and engineering that you can, and data processing and data visualization. It's a great model for for teaching the STEM subjects. Okay, this is just an example of the data we get. So this is a quiet day, not very much happening at all, as compared to the lower data, where we can see there's an event here, and there's the classic characteristic where the leading edge is very fast and then there's a decay. And we can see that the green is a completely different phase to the red.
And presumably you can correlate that to perhaps something that you've seen from, like one of the NOAA websites about, a CME or a flare or something.
Exactly.
Yeah.
Yes, exactly. Yes. Yeah, and if you're teaching coding and data visualization with MATLAB or Matplotlib, then again it's real data that your students can use to do that, and that's just a pretty one. It's the same kind of thing though. You get the idea. Geomagnetic observation, we got onto this, but it does give an excuse to use some of these NASA graphics that are spectacular. So this is planet Earth, and we can see here very beautifully how the magnetic field is compressed, distorted because of the solar activity, because of the CME, and that change is sufficient to be picked up with relatively simple. Yeah, there's another one. I just wonder what's going to happen to this satellite in 2 minutes' time. This is the again, it's a UCRA product. I think there's a probably better picture here. Yeah, so you can see it's quite simple. There's a couple, some stages of amplification. This one has an EEPROM on it to connect with some data.
Sorry, what's actually being monitored there?
The electromagnetism.
Okay.
Yeah, I think there's a couple of magnetoresistive components in there, which are
something like Hall effect devices or something like that.
Exactly. Yeah, I think that's what they use. And this is a sort of data. I just picked this up because this was some of my own data. We can see here that there's something happening around about 9 o'clock, and then I always have a look at other data sources, and we can see here a bit further north from the Institute of Space Physics in Sweden. We can see there that they have a recording an event. Okay, solar natural radio spectrometry. I've been talking a little about the violent eruptions from the sun, and we've already spoken of X-ray, ultraviolet, etc. But that also includes natural radio. And what we've got here is a broadband antenna pointing south. And this was set up in the autumn, so it's about 50 degrees. And as the sun travels through its aperture, so we can collect a natural radio spectrum. Again, just a simple box and a laptop's all that's required, as well as the antenna, and that's just we can see here. Mike, last autumn, your good friend Mike Naylor was helping me get this going, and we had a couple of bias tees just to power up some amplification up in the at the head amp. What we got here? Oh yeah, bias tee. Okay. And the sort of data we get, this isn't my data. Incidentally, but we can see here that we've got frequency in the vertical direction, and time is in the is on the x direction, and that's only about it's about a minute, I suppose, over 20 to 60 megahertz. And lot of real science on solar activity can be deduced from these spectra. This was one from just earlier in March, where we had one of our members recorded this just a 15-minute scan in the horizontal, but over 10 to 80 megahertz. Unfortunately, this was from my location in RG6, just at the top end of Pitts Lane, and there's just a huge amount of noise from broadcast TV channels, and Mike and I spent a couple of Saturdays setting this up and looking, because it was something that I was thinking at the time that I might want to take further. But for the moment, that particular project is on the back burner. But I do thank you, Mike. I learned a lot in those couple of days. And then again, from a good site, you can see solar radio bursts very easily. This was from Alaska, I think. One of our members is in Anchorage, in a very quiet, radio quiet location. Right, now this is something that is really really interesting, and something quite new. So cosmic radiation can come from outside the solar system. A supernova exploding will give a blast of cosmic radiation. I just got this example from the internet. Again, solar activity will give us cosmic radiation, and they're high. Basically, that cosmic radiation is high energy particles, protons, predominantly protons. And this is particularly interesting because it opens up another avenue of solar observation and correlation with other effects. So what's happening here? High energy, and we're talking hundreds of megavolts. They interact with the upper atmosphere, and we get these nuclear reactions occurring. So p-ions and neutrinos, which we've all heard about, but also muons, which are less common, but they're very easy is not quite the right word, but it's quite possible to detect them with a particle detector, which we'll have a look at in a moment. And one interesting thing is, and again, if you are an educator, this is fantastic, because a muon is, as I said, incredibly high energy, and it's traveling to all intents and purposes at the speed of light. Maybe 99.49 the speed of light, and in their own, in our time frame, they don't exist long enough to be measured. By the time they've been generated and get to ground level, in our time frame, they're gone. But because they're traveling at the very close to the speed of light, we get this effect of time dilation. So in their time reference, they do have time to travel from the point of being generated to the point of being detected. And Einstein described this and predicted this, but of course it wasn't until many years after his passing that it was established experimentally. But so if you want to talk about and discuss time dilation with your students, then this is just a great example. I won't go through all of that, but basically we can detect them with the Geiger-Müller tube, and from our wonderful friends in China, we can import a bag of bits, for £17 and put it all together. And you can see it's just very simple components.
So what's the actual detector? It looks like some kind of it probably won't be a vacuum tube. It'll probably be filled with some gas in which you're going to trigger.
It's a Geiger. It's a Geiger-Müller tube.
Right.
Yes, and it sits at something in the order of 300 volts. There's a DC converter on here somewhere. If a beta particle, a gamma ray, or a muon impinging within this envelope, then it causes an avalanche. Okay. And that produces a pulse. There's a bit of amplification, and we can count it. That's how a Geiger counter works. But the Geiger-Müller tube will detect all background radiation. So it will detect the beta and gamma and cosmic muon events. Now, it's only the cosmic muon events that we're interested in. So the way we eliminate the beta and the gamma radiation is by having more than one detector, so we can stack them. And an event that's registered on all the GM tubes simultaneously will be a cosmic muon event and not some random background event.
Are these tubes do they have to be physically located fairly close to each other, or do they have to be separated?
No, it's better to have them close together. In fact, you'll see a picture in a minute. I think it might be the next slide, almost. Yeah. So, but the problem, of course, is that when we put two tubes together, well, let me just go to the slide. We reduce the effective aperture of the detector, because anything coming from over here and hitting the GM tube, there's three here, but isn't going to be picked up by these two. There's only muons that come from within this area are detected by all three, which reduces the count rate significantly to only one per 5 minutes. And that's the stack that I built, and the tube sits here, and so an event that triggers all of them at exactly the same time, we've got some simple electronics to determine that, are counted, and we can count and display like this. Monitor the air pressure and the temperature as well. And all my experiments, I'd like to measure the temperature at the same time, because often you get temperature effects that you think are real events, and they're not, they're just drift. Oh, and that was the number of counts per day for that period in September last year. And then one of my colleagues supplied this data, and we can see that there was an event that was about 40 times over background. This is quite interesting when one can pick up something like that. So we have a STEM project because, as I said and noted earlier, that with the Geiger-Müller tube, the sensitivity is very low, and if we count cosmic events over a 5-minute period, we're only going to see one or two. And so a better technology would be a scintillator and a photomultiplier. But then that becomes, until recently, very expensive and quite complicated. But we've partnered with MIT, in fact, because they were concerned that their physics students, and I've heard this from people at Reading as well, are very keen to sit down at a computer and model an experiment rather than get a soldering iron out, build something, and make it work, debug it, and so this was designed by MIT for their physics students, and it's a single board with a it's got a small OLED display, Arduino processor, and it's a scintillator. So scintillators, as you can see, it's huge. I say it's huge in terms of the Geiger Müller tube that we were looking at earlier. I mean, it's 5 by 5 centimeters, and a centimeter thick. With one of these, and I'd never come across them before, having worked with glass photomultipliers for 40 years. The solid state is still a single photon counting device, and you can optically couple that to the scintillator, make the whole thing light tight, and run it through some amplifiers, and you've got yourself a particle detector. That reminded me.
Here's one I've made earlier.
Yeah, exactly that. Exactly that. So we are selling these as kits. I don't know if my lead isn't very long. You might need to swing the camera around, but I'm just going to put it in. Live demos are always a bit nerve-wracking, aren't they? Because they often don't work. I've lost my clicker. Where did it go? Is it working? Yes. So that's just one detector. The black block at the top is the scintillator wrapped up in plastic tape to keep the light out. And each flash is either a cosmic muon, a beta event, a beta particle, or a gamma event, just from the building materials or the geology or whatever.
Anyone got a watch with a radioactive dial?
Yes. So,
do you want to put it next to it and see if it has any effect?
So we're supplying these.
I think they're mostly alpha particles, though, from the watches. Probably wouldn't get through the.
Yeah, it won't pick up alpha, but if it's got, is it a luminous watch? Yeah. Yeah,
they're mostly alpha particles from the luminous watches.
It is, but we have had. Let's hit it on top. It integrates. If it changes, there's a little bit of gamma from the radon. So if any of you've got contacts, or you work with, yeah, I think you had to leave there for more than a minute. Yeah, it won't pick up alpha, of course, but we're looking to introduce these into the UTC sector. We've been talking to Reading and Oxford, in fact, because it incorporates so much for a student to get to grips with, particularly if you're starting with a, I think I might have a, oh no, I haven't got it here, a bag of components. And there's quite some sophisticated, a lot of the electronics is on the other side of that board, and it's surface mount. So it is quite challenging for a student, but nevertheless a good thing to do, and build something that is going to actually work and do stuff for you. There's you can take the data out through the USB serial port, and there's Python code that can be written for data visualization, teaching coding in a real-world situation. Okay, hydrogen line observation. This isn't Brian's setup, although Brian was here earlier, as we mentioned, but this is Peter East, and I like this because he's got a home-built antenna there that's not that, I mean, it's a lot more complicated than anything I've built, but it's not overcomplicated for what we're doing here. And then he's got a couple of amplifiers and a filter, and can get these traces as as the Earth spins round, and then he changes the angle, and then it comes again, and so we can build up this the set of curves as the telescope runs through one of the spiral arms of the galaxy. With more data got there. You've probably seen that again. That is Brian's antenna in his front garden. He probably showed you that. He's been doing radio astronomy, and he's a radio amateur, of course, as well, for a very long time. Yeah, more of the same. And then Lawrence, a friend of ours, he's in the process of building some dishes to do hydrogen line work as well. But what one can do is take the signal from two dishes and have a phased array, and we can have an effectively much larger aperture for our observation, and not only a larger aperture, but with a greater sensitivity. We're getting to some really advanced stuff here, but again, it is possible with quite simple kit, but with some quite advanced signal processing to observe these pulsars. And, oh yeah, doesn't always work, but it's working today. It's a nice little GIF. So what we've got here is, this is with Peter East. So he's got his antenna, low noise amplifier filter. So all that's kind of base standard stuff for radio astronomy. But then he's got these very, he's written some very clever software to sort out the signal from the noise. And the suite of programs that he's written are used by professional astronomers. So we can see what looks just like noise. There's no arguing that there's a real signal there. So I think he can take a profile like this, and of course there'll be many of those going down here, and then fold them over.
Oh, it's like a correlation over time.
Exactly that.
Yeah.
It's a correlation over time, such that we then get, he can then get this. And this is detecting pulsars with, with an antenna that is, it's quite modest. And coming up towards the end, I don't know how long I've been talking, but fast radio bursts. So these are quite a new phenomena. Only first observed in 2007, but they're extremely fast and have massive energy. And you can see the signal strength is the same as 1,000th of a mobile phone sitting on the moon and receiving it here. It's really small. And also you have to be pointing, you have to be looking at the right place in space when it occurs. But this is where we started. And these guys here are working with world leaders in this particular observation of very fast radio bursts. We're only looking at some milliseconds, but of course they could happen anywhere in the sky. And sometimes an object will emit a fast radio burst and then be quiet for many days, and then suddenly another one will appear from the same object. It's really quite fascinating. Okay, yes, and here we are. They're extremely fast. This was the first one that they observed at this observatory, and that's the information relating to it. Okay, so in conclusion, the independent researcher can do a lot with very little. it offers opportunity, of course, as I've mentioned several times, for you to develop skills in coding, surface mount soldering, getting stuff working. And it's a great fit with amateur radio, in fact. I think half our members, maybe more than half our members, are also radio amateurs. Great for citizen science and STEM projects. And we have a very active group within the BAA. And I always put this comment in when I'm talking to astronomers that use, the classical astronomers with a telescope, because they're only looking at a really small part of the electromagnetic spectrum. But of course, as radio astronomers, we're looking at far, far more. And as I started at the beginning, it does complement and add to our understanding of the cosmos. I mean, even today, as I mentioned, 6 o'clock news, at the head of that bulletin, there was the observation of that supermassive black hole, 60 million kilometers across. First time, they'll probably get Nobel Prize for that image. Thanks for your attention. I feel like I've been talking for days. You're still awake anyway, so thank you so much. Thank you for your time.
Yes, so on behalf of all the members, both here and in the virtual world, thank you very much for a fascinating talk, and you get extra brownie points for doing a live demo, which is working, so well done for that.
Not always.
So we'd like to, if you're happy to, if there's any questions, have we got any questions on the floor?
Yeah, I was just going to ask whether you get involved in, unfortunately, Arecibo sort of suffered a sad demise. But
absolutely, yes.
I believe that the Chinese are, I don't know whether it's come online yet, but I believe they are constructing what is going to be one of the largest radio telescopes.
Yeah,
I wondered whether, in fact, your members, rather than actually just being involved in effectively trying to build their own detectors, would be involved in trying to assist in the analysis of data, because there's obviously a huge amount of data that can be collected from these large arrays.
Yeah, that's a good question. That I don't know. The telescope you're referring to in China, I don't think is online yet, but it will be. It's kind of imminent.
Yes.
We do have quite close links with the Society of Radio Astronomy in America. And I know there the lines between the amateur and the professional are less blurred. But we're building really good connections with academia in the UK.
Okay, thank you.
Any further questions from the floor? Mike?
Well, I heard of something called the Square Kilometer Array.
Yes.
Australia, was it?
Yes.
Or is that still going?
Yes.
Or, and is that something that amateurs could be involved in at all?
No.
No.
The problem is there's a number of experiments like the array you mentioned, but the data sets that come off these things are absolutely vast. There was, I don't think it was that one, it was one in Canada. They were talking about the data processing, and these things generate each, because they're looking at a broad spectrum and sampling so fast, the data sets that are coming off of a single telescope are like terabytes per day, and it's an array of maybe 100, and so the data processing and the data communications becomes a real problem. And they were talking about using AI for data analysis, because the data sets were so huge, petabytes of data. That
I think there's an array also in Texas. And each detector looks a bit like a bedstead, but it's essentially some kind of VLF detector.
Yes, it's upside down. Yeah.
Any further questions from the floor? No. Any questions on the virtual side there, Tom?
Just if anyone wants to ask a question, just pipe up now.
Right, okay. Well, in that case, it's my pleasure. Well, first of all, another round of applause, please, for Paul. Thank you very much.
Thank you.
Distinct advantage of being in this hall is that there's a great number of jammy dodgers and other luxurious biscuits and tea and coffee, which we'd like to invite you to enjoy with us and join us for a general chat.